you were forced to think outside the box in order to come up with a new thing. No, by the way, the Veritasium video, he's a guy on YouTube who does a lot of sciencey stuff, and he answered that question that someone posed. And he actually, just like me, got it wrong. Now, unlike him, I do not have a PhD in physics, so the fact that I have 3 years of physics experience and he has like 12. So the fact that people who have experience in physics still get these problems wrong because it's hard to focus on a new perspective. Okay, so there's a few people I'd like to, old people, dead people, ancient people I'd like to share with you. Basically, these people change the perspective of their own world to yield the result that we take for granted nowadays. So, first one I'd like to talk about is Zeno of Elea. Elea is the town he was from. He lived about 2,500 years ago, and he actually inspired Aristotle after Aristotle was a well-established philosopher to change his perspective on the way the world works around us. Now, Zeno had 10 paradoxes. I'm not going to go through all of them, that's insane. Instead, I'm going to go for the first couple. So the first paradox is Achilles, so the famous runner and warrior Achilles, versus a tortoise. Obviously, we think intuitively that the man is going to win. But Zeno showed in a certain mathematical way that in order to catch up to the tortoise, he has to get to the same position as the tortoise. But the position is always changing because both the man and the tortoise are moving, so he can never have a hope of catching up. Now, that's, again, weird, because of course a man can outrun a tortoise, but it's to shift perspective and say, well, at the time, 2,500 years ago, our math was not up to par enough to answer simple questions like how did you win a race? Another thing that came into play later, until general relativity came around for Einstein, was his arrow of time paradox. If you had a really fast painter who could paint instantaneously, so basically taking a picture, an archer fired a bow, and an arrow is flying through the air. You'd have a snapshot of the arrow as it's traveling in space. Now, of course, we see the arrow moving, yeah, relative to everything else. However, the painter doesn't. The painter sees everything stationary at all times. So the question he asked was, how can there be movement if all things are frozen in a single instant of time? Well, as Bradley Dawson at CSU Sacramento establishes, this thing had a very incredible impact on the foundation of calculus, which is the math that we use for the modern world that we take advantage of today. Another man by the name of Nikola Tesla also used this idea to create alternate current relative to direct current. I'll just quickly explain the difference. So direct current is basically like if you hook a battery up to something that consumes electricity, it goes directly from point A to point B, nothing fancy. However, it's problematic when you want to go long distances because you have to short down the voltage, otherwise you're going to get shocked. So alternate current is what we use in the modern world, which is electricity, think of it as vibration, so it goes back and forth. It still goes from point A to point B, but it does so in an oscillatory fashion, which is not as intuitive as people would think. This really solidified under the direction of Albert Einstein and his photoelectric effect, who proved the experiment that I have on my t-shirt wrong, actually. This I have on my t-shirt is called the double slit experiment by Thomas Young in 1801. Thomas Young showed that waves are the way that light propagates through the universe. It's similar to a petal falling into a pond, where you see the ripples of the water fan out infinitely. But Einstein said, no, that can't be right. I'm noticing things that aren't consistent with that. Just like the tortoise can easily be overrun by the man. It's not consistent with our observations. So we have to shift our perspective to get an idea. So he came up with what's called wave-particle duality, which basically means that light is both a wave and a particle. Instead of it being a continuous thing like waves and water, pebble, it's actually individual tiny particles lined up. But there's so many lines linked to each other, it looks like a wave from our bigger perspective. The reason why that's important is because that's the exact math that is in touchscreens, that is in computers, that is in every single thing that we use. In fact, these lights in this room would not be possible without both the inventions of Nikola Tesla and the photoelectric effect from Albert Einstein. So, let's reflect on that demonstration a little bit. It was a simple demonstration, and literally had someone drop something. They can't get any simpler than that. However, even in the simplest of things, the things we take for granted, things like the leaves and trees even in nature, we have to look deeper if we want to understand them. And in order to look deeper, we should think about how to dissect them in a different light, a different viewpoint. So we are often hinged by our temptation to be, I'd say, intellectually lethargic, right? It's easy to say yes or no instead of critically thinking about something. But instead, we should think that a shift in perspective is what gives life.